Okay, so section 5.5 deals with finding eigenvectors when you have complex eigenvalues. So if your eigenvalues are complex, the eigenvectors are going to be complex. And it is important, like up to now, when you've had to find eigenvectors in chapter 5, you dealt with real eigenvalues. But now you're going to find eigenvectors for complex eigenvalues. Let me give you a moment to copy this example down. Okay, and one moment here. Okay, so for this problem, like the eigenvectors, like normally we would say the eigenvectors are in two-dimensional real space. But because the eigenvectors are going to be complex, we say the eigenspace, well, the eigenspaces are going to be in two-dimensional complex space. And that's how we denote that for two-dimensional complex space. So what's the first thing we need to do, class? What's the first thing we have to do to find the eigenvectors? Well, we have to find the eigenvalues. So let's go ahead and do that. So, of course, we have to solve the characteristic equation. And since this is a 2 by 2 matrix, you can get the characteristic equation and use quadratic formula or factoring. In this case, we have to use quadratic formula to solve for the eigenvalues. So let me just give you a moment to copy down what's on the page here. I don't think there's, if you have any questions, please let me know. I don't want to, I like to, I think you know how to do this part. So let me know though if you have any questions. All right, are there any questions? Now that we've found, well, I mean, of course, our eigenvalues, lambda, we need to simplify this expression here, and we can certainly do that. But are there any questions so far? May I move to the next page? All right. So our eigenvalues are going to be lambda 1 equals 2 plus 3i, and lambda 2 equals 2 minus 3i. And now we have to find our eigenvectors. And we find our eigenvectors the same way that we found our eigenvectors when we dealt with real eigenvalues. We have an augmented matrix that we have to solve. Okay, so let me let you copy up to here. And let me know if you have any questions. Okay, so, well, all right. I mean, the A minus the quantity 2 plus 3i times the identity matrix. So the diagonal entries are what are going to be changed here of A. You know, the negative 2 and the 5 are as they are, but I took then 1 minus the 2 plus 3i times 1, and I took 3 minus 2 plus 3i times 1, and then that gets me down to here. And the thing is that you know, just like, again, just like when we work with real, you know, this augmented matrix has complex numbers in it, right? You're used to augmented matrices that have all real numbers in it. Now we're doing a matrix that has complex numbers in it. But the row operations you do are going to be, you know, it's the same goal as, you know, as you've always had. We want to try to get the matrix in reduced echelon form. And so I'm going to actually here, let me see here, one moment now, class. All right, so if I take the first row, here, let me maybe put this in blue. if I take the first row and I multiply that by this scalar, -1 plus 3i over 5 times row 1, and then add that to the second row and replace the second row by that result, I'm going to end up with zeros in the second row. Now, one way to help you see this is if you take -1 minus 3i and multiply it by -1 plus 3i, that's going to equal 10. Because if I FOIL this, the -3i and the +3i cancel out. And what class is I squared equal to? What's I squared equal to in complex? That's right, Benjamin, -1. So this is like 1 minus 9 times -1. That's going to be 10. And so you're going to have 10, but you're dividing that by 5, right? What I'm trying to say is the scalar you're multiplying the first row by is -1 plus 3i divided by 5. So effectively, you're going to be adding 2, since 10 divided by 5 is 2, you're adding 2 to -2, which gives you 0. And then 5 times -1 plus 3i times 5, this part here, that's going to equal 1 minus, that's going to equal -1 plus 3i. You add that to 1 minus 3i, you get a 0. Okay, so are we okay? Are you okay with how I got the zeros here on this bottom row using this row operation? Are you all right with that? The goal of course, is to produce a 0 in where the -2 is, using -1 minus 3i as a pivot. Well, it turns out that if I take -1 minus 3i and multiply it by -1 plus 3i over 5, that's going to be equal to 2. Okay, that's going to equal 2. The numerator will be 10, the denominator will be 5, and that will give you 2. And then, okay, and then you add it to the -2, and you get the 0. And it turns out also, coincidentally, you get a 0 here. And that's no accident. That's no accident. When you do row operations, okay, with these complex, like we're doing here, with the complex number in it, in the end, you're going to get, well, let me say it right here. You started off with these 2 rows, right? These 2 rows, and those rows correspond to equations, right? Those rows correspond to equations. Well, it turns out those 2 equations are redundant. They're redundant. In other words, we do not need, well, and you can see that by the fact that after you got done with your row operations, the bottom equation is all 0. Like you're only left with 1 equation, right? That means if you start with 2 equations and you do row operations, and you're only then, when you're done, left with 1 equation, then the 2 equations are redundant, and this is no accident. Like when you have complex numbers, if you know one complex number, you know the other. How many remember that, like, complex solutions occur in conjugate pairs? How many recall that maybe from their pre-calculus days? Like you solve well, I mean, look what happened with our quadratic equation, right? We solved it, and we got two solutions. Negative, we got 2 plus 3i and 2 minus 3i. Well, it also holds that when you solve this homogeneous system of equations, the two equations are redundant. And so you only really need to utilize one of them to find your eigenvectors. Are there any questions so far? Please let me know if you have any questions. Okay, well, what I'm going to do, given, does it make sense? Does this make sense that the two equations would be redundant because you're dealing with complex solutions? How many have kind of an intuitive feel, an intuitive appreciation for that? Well, I was hoping maybe one of you would. um, well, let me ask you this. If you know one complex eigenvalue, do you automatically know the other? If somebody were to tell you, okay, this matrix A, one of the complex eigenvalues is 2 plus 3i, does it follow that then that you would know the other complex eigenvalue? It does, Nafati, absolutely. And so similarly, when we set up the two equations, when we set up our augmented matrix, the two equations, well, I want to say this the right way. This is maybe not a good analogy. Eventually, you're going to have an intuitive feel for this. But what I'm trying to say is, when you have a complex eigenvalue, and you're going to go solve for your eigenvector. For a 2 by 2 matrix, you have two equations that you're solving for. And what I'm telling you is, we only need to use one of the equations. We only need to use one of these equations to find an eigenvector. In other words, to find the eigenvector, we need to solve for x1 and we need to solve for x2. And we only need one of these two equations to solve for the eigenvector, to solve for x1 and x2. So what I'm going to do is, I did row operations down here to show you what would happen. But given we know that these two equations, 1 and 2, are going to be redundant, we only really need to use one equation. And I don't even need to do any row operations then, right? I can just use the one of the equations. So which equation do you like better? Do you like the equation, the first equation? Well, actually, hold on. I actually want to go here, right? Because here, this is where we did the subtraction. Here's the first equation. Okay. And here's the second equation. And I want to solve, again, I'm trying to find an eigenvector, so I got to solve for x1 and x2. So which equation do you want to use? Do you want to use the first equation or the second equation? Which equation looks more attractive? Which one do you like better? Okay, I agree. I agree with Nafani and Ariana, the second equation. And so that's what we're going to use. Since we have two redundant equations here, you know, -1 minus 3i times xi plus 5x2 equals 0. And the other equation is -2x1 plus 1 minus 3i times x2. I'm going to use the easier one, and that's what I do. So on the next page, here's the equation, and I'm going to solve for x1. And x2 will be free. I solve for x1, and x2 is free. Please let me know if you have any questions, okay? Okay, so now what we need to do is, now that we have solved for x1 and x2, we can go ahead and put down our eigenvector. And I have that on the next page. So may I go ahead and do that? Are there any questions here? So x1 is 1 minus 3i over 2 times x2, and x2 is free. Okay, well, then the solution vector x consists of the components 1 minus 3i over 2 times x2 and x2. And I'll factor out the x2. Okay, and so this is my result. Now I don't want to have any fractions for my eigenvectors, so I can choose my first eigenvector to be to have components 1 minus 3i and 2. So what did I let x2 equal then to get this nice eigenvector? Well, there's no fractions in V1, no fractions in the eigenvector V1. So what did I have to let x2 equal here to get eigenvector V1? x2 is a free variable, right? That's right, Nafani. Let it equal 2. So I found one eigenvector. And we're going to do the same thing. We're going to do the same thing for the other eigenvalue. Okay, the other eigenvalue, we're going to find the eigenvector corresponding to the other eigenvalue. Now let me ask you this. Just going to ask you. What do you think an eigenvector corresponding to 2, given that an eigenvector corresponding to the eigenvalue 2 plus 3i is this eigenvector v1, what do you think an eigenvector would be corresponding to the eigenvalue 2 minus 3i? Can you maybe make a guess? Okay, so take a moment here to think about it. Let's see. Hold on, we got a response here. That's right, Benjamin. That's right. See, the eigenvalues occur as complex conjugates. The eigenvectors are also going to occur as complex conjugates. If you know, just like if you know one eigenvalue, you know the other eigenvalue. Same thing, if you know one eigenvector, you know the other eigenvector. But what I do to be a little bit formal is I go ahead and I do the, hold on, let me get this email off here. I don't want any distractions. One moment, class. Sorry. Okay, so if you were to try to verify that this is an eigenvector v2, which equation do you want to use? The first equation or the second equation in this for this system of equations? Which row do you want to use? The first or the second row? Well, which row looks nicer? Hold on. I agree, Ariana. The second row, and that's what we're going to do. So we'll use the second row. All right, if we do that, here's the second equation corresponding to that second row. Okay, and you do a little bit of math and you solve for x1 and x2 is free. And then you substitute them, you now have your solution vector x. And sure enough, the eigenvector corresponding to lambda equals 2 minus 3i is going to be the complex conjugate eigenvector. Absolutely fascinating. And this, you're going to be using these, like actually, I don't know if well, if you take differential equations, Math 282, you learn at the end of the chapter that solutions to systems of differential equations, systems of linear differential equations, or I guess they call it linear systems of differential equations, they involve eigenvectors and eigenvalues. How many remember that maybe if they took Math 282, differential equations? Okay, Benjamin remembers that. And you know, in that course, when you learn that, you know, you sort of took it on faith. They gave you formulas, and you just kind of mechanically did the problems. But in this course, you're going to understand why that's true. And so, of course, you know, we have to be able to work with real and complex eigenvalues and real and complex eigenvectors. You know, so all right, give you a moment to copy this down. All right, well, are there any questions at all? What I want to do then, I want to bring up the ebook and look at a few examples in there. And so let me do that next. One moment. Okay, let me get that ebook up now. Okay, so all right. So they mention here that, hold on. I'm trying to get this to, all right. This is the important sentence here with complex eigenvalues. So, but let me see here. Do we need this? Can we get rid of that? Yeah. I like making it bigger, the print, but then I gotta, make adjustments in the window. So, they're saying in section 5.5 that our interest in complex space deals with the study, the study of complex eigenvalues is essential in order to uncover hidden information about certain matrices with real entries that arise in a variety of real-life problems. Such problems include many dynamical systems that involve periodic motion, vibration, or some type of rotation of space. So a good example of this would be you could have a system of a linear system of differential equations, and you're solving for x and y, and the solution set for x and y involves a solution that rotates, that involves sines and cosines. Okay, how many maybe have seen that in Math 282, differential equations? How many have seen that? Who've taken differential equations, so remember that. Okay, Justin remembers that. Good, good. Nafani remembers that. Well, again, you're going to understand why it's true now. Well, not right now, but very soon. Okay, when we get to section 5.7. Okay, so they have some nice examples. They mention here. They give a little matrix A here, 2 by 2, and this matrix A rotates the plane counterclockwise through a quarter turn. So remember, anytime you have a matrix A and you multiply that matrix A by a vector, you're doing a transformation on the vector. Well, what is the transformation? Is it a reflection? Is it a rotation? You've seen these different types of transformations. Well, what it turns out that this matrix here, it's going to be a rotation counterclockwise through a quarter turn. But in fact, what's also true, and you've seen that kind of thing before. I mean, you know by looking at a matrix how to identify what transformation it's doing. But what's interesting too is if you look at the characteristic equation here, which would be, you can just take the determinant of A minus lambda times the identity, you'll get lambda squared plus 1 equals 0. But for this rotation matrix, it turns out that it has complex roots. So that is no accident. That is no accident that would happen. Okay, no accident that would happen. In the second example, they go through a process where they want you to find a basis for each eigenspace. This example is just like the one that we worked out. I mean, it's a different matrix A, but the concepts are the same. So let me go forward here to example 3. Let me move to example 3 here. Yeah, this is. So they mentioned that one way to see, let me try to highlight that all. Yeah, one way to see how multiplication by a matrix A, well, okay, in the second example, that matrix A from the second example, how does it affect the points is you can take some initial point and then plot successive images of the point under repeated multiplications by this transformation matrix A. So in example 2, the transformation matrix A, okay, was had entries 0.5, negative 0.6, 7.5, and 1.1. And you multiply that by 2, 0. It takes 2, 0. See in the picture below. Okay, hopefully, let me see if that all shows here. I might have to, can I make it a little smaller? Okay, that's fine. So in the picture below, the x sub 0, that vector, is at 2, 0. when you multiply it by a, it moves that point to the point x1, to the vector x1, which is 1.0 and 1.5. Similarly, if you take x1 and multiply it by a, okay, you'll get the vector x2, okay, and x2 is going to equal the vector with components negative 0.4 and 2.4. Well, x2 they showed in the picture there how x1 got rotated to x2 or moved to x2. So if you continue this process and successively multiply the previous vector by the matrix A, what's going to happen is the effect, hold on here, the effect of that is going to be the sequence of these vectors lies along an elliptical orbit. An elliptical orbit. Okay, that's the effect of it. So, are there any questions on that? Any questions on that idea? All right. So what I'm trying to make clear here is that if a matrix has complex eigenvalues, the transformation is going to be effectively a rotation. All right, let's continue on. If you're good, let's continue on through section 5.5. Let me keep going here. So of course, vectors, just like complex, sorry. So just like complex numbers can have real and imaginary parts. Okay, so like 2 plus 3i. Well, 2 is the real part of that number, and the 3i is the complex part. Well, with vectors, you can have real and imaginary parts of vectors as well. So, in example 4, here is a vector, okay, that vector x that has components 3 minus I, and 2 plus 5i. And what you can do is you can rewrite that vector as a real vector plus I times another real vector. And so the real part of the vector is 3, 0, 2, and the imaginary part of the vector is negative 1, 1, and 5. Okay, and then you can have a complex conjugate of a vector. The complex conjugate of the vector would just be the complex conjugates of all of the entries here in X. Okay, so that's just some notational information. Okay. All right. Are there any questions on this? All right. Trying to keep things intuitive and simple. All right. Let's continue on. Let's do a little more here. So in example 5, the matrix in example 2 yielded these complex eigenvalues, 0.8 plus or minus 0.6i, and these complex eigenvectors. The next example provides the basic building block for all real 2 by 2 matrices that have complex eigenvalues. Okay, so what they do is they have a matrix C, okay, that consists of those entries. Okay, so in example 6, look at the entries there, and I'm just looking at one thing here. Okay, let's say in example 6, that your entries were like this. Okay. Well, the eigenvalues can be shown to be lambda equals plus or minus a plus or minus b times I. And the if we plot the complex eigenvalue, do you remember? Did you learn in high school that to plot a complex eigenvalue like a plus bi, you plot the coordinate a, b? How many maybe recall that from high school? Seeing something like that. Okay, Benjamin recalls it. Haley recalls it. Okay, Eleanor recalls it. All right, well, we're doing the same thing here. And so, but you see, what you can do is thank you, everybody. So what you can do is you can take the matrix C, and you can actually write the matrix C as this radius R. Okay, we call R the radius, and write the radius R times that matrix there, where you have A over R, negative B over R, B over R, and A over R. Okay, now let me just, yeah, that's true, because you're dividing through the entries in the matrix by R, but then you're multiplying by R, so that's true. And then what you can do is you can decompose that this way. Okay, so I want to say this the right way. One moment, class, one moment. One moment. I just want to check one thing here. Yeah, so you see based on the picture, okay, that angle, var theta, okay, I'm trying to recall that symbol. I believe it's var theta. The angle var theta. Let me just go right to here. Hold on. Okay, so let's see. I got to make sure what I want to highlight here. I mean, I know what I want to do. I just want it to be right. So, okay. Now, how are they getting? Well, no. Let me do it like this. How are they getting cosine of var theta here? How are they getting that? How are they getting the cosine of that angle? Well, the first entry, okay, the first entry here is A over R. Okay, A over R. So based on the picture, if you look at A and you look at R, how is the ratio of A over R defined? Cosine, that's right. That's right. Good, Nafani. So the cosine of var theta would be A divided by R, but R is, well, so hence cosine of phi is A over R. Let's look at the sine of var theta. In the picture on the left, how's the sine of var theta defined? What would the ratio be? Sine is opposite over hypotenuse, right? So that's right, Nafani. Sine of R theta is going to be B over R. So hence, you see, B over R goes with sine of var theta. And you could verify the other two, these two as well. Okay, so what you're doing here is, given this deconstruction of the matrix C, given this deconstruction, you recognize C, okay, as the matrix C, and I want to say this the right way, hold on. What is the effect of, what is the transformation induced by matrix C? Well, the transformation induced by the matrix C is to rotate, okay, var theta, an angle var theta, okay, shown in the picture there, counterclockwise, between the positive x-axis and the ray from 0, 0, hold on, the ray from 0, 0 through AB. So the angle var theta is the angle between the positive x-axis and the ray from that connects 0, 0 to AB. Okay, and then, of course, you're going to have a scalar multiplication of R by all the components. Okay, so let's see here. I'm just checking one thing, class. How many think that's pretty cool? Pretty cool, that analysis. I mean, effectively what we've done is we've said that the transformation can be viewed as a composition of a rotation through an angle, var theta, and a scaling by the modulus of lambda. The modulus of lambda is R. Okay, how many have heard of the word modulus before in terms of complex variables? Okay, Benjamin has, Shivani has. Okay, great, great. And all right, so I think Benjamin and Shivani are liking this. And it's always a beautiful thing when we can look at these matrices, when we can look at them, and studying the transformations of matrices on vectors is also a very important piece of. It gives an important information to us. And actually here, they show a little picture here of what's going on. Okay, they're showing a little picture there of what's going on. So I'm content right now with what we've covered in section 5.5. Do you have any questions for me at all? Okay, let me stop the recording.